Okay, this is lecture 10b. This is continuation of what we were just talking about with derivatives of polynomials, and now we're going to turn our attention to derivatives of exponential functions and then a bunch of examples. So what's an exponential function? Well, we've been playing with functions like 2 to the x, 5 to the x, 2 to the minus x. All of these things are exponential functions. What makes them exponential functions? The x is, or the variable, is in the exponent. Anytime you have a variable in the exponent, that makes it an exponential function. So don't confuse exponential functions with polynomials. What's the difference between x squared and 2 to the x? Well, the graph of x squared, okay, if I draw the graph of x squared, you should all know that x squared is going to look like a parabola. But the graph of 2 to the x is going to be asymptotic on the left, and then it grows very rapidly here. So exponential functions have that basic shape, and polynomials have this basic shape. The domain of a polynomial is all real numbers. There are no asymptotes. I can plug in every possible real number, and I get y values. For exponential functions, I can also plug in every number, but exponential functions are asymptotic. As x gets more towards negative infinity, 2 to the x gets closer and closer to 0. Okay, they have totally different characteristics, and as we'll see later, exponential functions win hands down in a race. They get big very, very fast. Polynomials are slow by comparison. All right, so we need to calculate the rate of change. I mean, how else are we going to figure out how fast they grow if we don't measure their rate of change? So let's take an example. Actually, what I want to do is I want to do them all at once. I want to look at a function f of x equals b to the x, where b is any constant number. So think, for example, 2. B stands for base, all right? And what I want is the derivative of f. So how do we take the derivative of this? The high school rule is a fail. If you write x times b to the x minus 1, you fail. That's like, that's one of those errors where I will take points off from other problems if you do that. Exponential functions do not have the high school rule to tell you how to take the derivative. So how do we take the derivative of exponential functions? Well, all we have right now is the definition. So we just write it down. It's the limit as h goes to 0 of f of x plus h minus f of x over h. Well, we know that, so let's calculate f of x plus h. That means replace x by x plus h wherever you see it. So that's going to give us b to the power x plus h. And then we have to subtract f of x, which would be b to the x. And all of that is going to be divided by h. So far, so good. Well, that's the limit as h goes to 0 of what? Well, can I factor in the numerator? Well, it turns out, yes, I can. I can factor out b to the x. Now, do this carefully. What does b to the x plus h mean? Well, there's a law of exponents that says, if you remember, right up here, a to the x times a to the y. When you have two exponential expressions multiplied together with the same base, you get to add the exponents. So I'm going to use that law backwards to factor a to the x plus y, or in particular, b to the x plus h. So it's b to the x times b to the h. So the b to the x gets pulled out, and that leaves you with b to the h in that first term. And when I factor out b to the x from b to the x, that just leaves 1. Right? Now, if you don't believe it, just go ahead and multiply this out. Multiply b to the x times b to the h. Use the law of exponents, and you get b to the x plus h. Then b to the x distributed against the 1 will give you minus b to the x. Okay, we still have to divide by h. Okay. Now we get to an interesting question. What's going on as h goes to 0? What happens to b to the x as h goes to 0? Do you see any h's in this b to the x? The answer is no. There are no h's in b to the x. So as far as b to the x is concerned, h is just independent of it. So another way to say it is that b to the x could be considered constant relative to h. So if h is moving, b to the x doesn't do a thing. So we have a theorem that says that the limit of a constant times a function is the constant can come right out. So the constant just sits there and watches while we take the limit of the other stuff. So this is b to the x times the limit as h goes to 0 of b to the h minus 1 over h. Now, I just want you to take this whole thing and think of it as one quantity. Okay? Now, it's a 0 over 0 bad news type of thing, but let's just forget about that for a minute. Blur this, just sort of take it out of focus for a minute and think, what's it going to be in the end? What kind of a thing is it? Are there any x's in here? The answer is no. So when you let h go to 0, this thing will give us a number, assuming the limit exists. Okay, I'm going to jump ahead and tell you, yes, this limit exists. It's not going to be infinite, so it's a limit. It also won't be 0, much to your chagrin, but it is not. It is some other number. You're not going to like what the number is, but let's put that off for the time being. All you got to know right now is that this is a number. Think of it as a constant. Okay, so I'm just going to write a big K in here. It's a constant. All right? But what have we got? The derivative of this exponential function is that exponential function back again times some ugly constant that we can't figure out. So let me summarize that. The derivative with respect to x of b to the x is b to the x back again, back at you, times some constant that I'm not telling you what it is. Now, I really should tell you a little bit about this constant. If we look at this thing, even though I've mucked it up a little bit, let's look at that. It looks familiar, doesn't it? Limit h goes to 0, b to the h minus 1 over h. Looks like a difference quotient, doesn't it? It certainly is. It is, in fact, the derivative of this function at the point where x equals 0. If you were to write f prime at 0 for this exponential function and write it out in the h form, this is what you'd get. So this quantity, if you just look at it right, it's f prime at 0. And what is f prime at 0? Well, we don't know, but I can draw you a picture. Here's the graph of b to the x for normal values of b like 2 or 3 or 5. Okay, it's an exponential function, right? F prime at 0, this is our f. F of x equals b to the x. What is f prime at 0? What does that mean? It means the slope of the tangent line right there. What is the slope of that line? Well, I can't tell you what that is right now. It depends on how steep this thing goes up. You remember the graph of 2 to the x, 5 to the x, 10 to the x? Well, one of these days in the lab, we'll zoom in on this and figure out empirically what the slope of that line is. But I can tell you that there is, well, what would the nicest number that you could have here be? What would the slope, what slope would you like to have there? What m would be the nicest one? Now, 0's out because you're never going to get 0 slope. It's not going to turn around like this. It's going to be asymptotic here. So you're always going to get a positive number for the slope. So given that, what positive number would you like the slope to be? Well, you're not going to get lucky enough that the derivative of all of these guys is the same answer. It is not. 2 to the x is going to have a shorter slope, a smaller slope than 5 to the x. 5 to the x goes up faster. 10 to the x goes up even faster. So those m's will be bigger. So this number will depend on b. What number would you like this slope to be? Well, I've been leading you to it. I would really like m to be 1. I want m to be 1. So is there a b that would give us an m of 1 for the slope of the tangent line at 0? Well, sure, there is. What is it approximately? Well, I can tell you that if you try 2 to the x and you measure that slope, just measure it on a computer, see what it is, you'll find that the slope is a little less than 1. If you go to 3 to the x, your slope will be a number bigger than 1. So somewhere between 2 and 3 for this b is the function who's got a slope exactly equal to 1. Well, you might guess what that number is. It's e. And this is the definition of e. It's the special base where the function e to the x happens to have a tangent line at 0 that is of slope 1. And this is so wonderful because what does that say about the derivative of e to the x? It says that the derivative of e to the x is e to the x back again times this constant, where this constant is the slope of the tangent line at 0. But I told you e to the x was picked, e was picked so that it would have slope at 0 equal to 1. So the derivative of e to the x is e to the x times 1. So ladies and gentlemen, here is a function that is equal to its own derivative. In English, this says the growth rate of the function e to the x is exactly equal to the y value. If you want to know how fast an exponential function e to the x grows, you just calculate its y value. The y value is also the slope of the tangent line. That's pretty cool. It's a very, very special function. It is the most important function in all of mathematics. It has been called that. The most important function in mathematics. Okay, so you need to know about the derivative of e to the x. And we'll come back and talk much, much more about exponential functions. Time to turn our attention to a bunch of problems. So let's calculate nothing more than derivatives, and these are very much like homework problems. Okay, so let's start with the derivative right here. The derivative of, how about e to the 5th? Here's a problem. What is the derivative of e to the 5th? And this is a trick question, folks, so don't answer too quickly. The derivative of e to the 5th is, well, some people are going to use the high school rule and write 5e to the 4th. Wrong, even though this is a constant. Some people are going to say, well, I just had e to the x. The derivative of e to the x is e to the x, so the derivative of e to the 5th is e to the 5th. Wrong. What kind of a thing is e to the 5th? The answer is it's a number. Do you see any x's in there? E to the 5th is a constant. It's the kind of thing you can punch into your calculator. So it's somewhere around 30, 40, 50, something like that. More than that, but less than 100, I think. In any case, it's a constant. So the derivative is 0. Derivative of e to the 5th is 0. Trick question, but please be aware of that. You will probably see that on an exam or something like that. Just because it's got a power doesn't mean you use the high school rule or the power rule, and it doesn't make it an exponential function just because it's e to a power. Okay, how about the derivative? Well, you already know the derivative of e to the x. How about the derivative of x to the 5th? Well, high school rule, 5x to the 4th, because 5 is a constant. So the derivative of x to a constant, you can go ahead and take it using the high school rule. How about the derivative of x to the e? Well, once again, what is e? E is not a variable. E is a constant. It's about 2.7. E is approximately 2.7. So this is just x to a constant. So yes, the high school rule says the derivative is e times x to the e minus 1, whatever that is. Okay, and that's a perfectly good answer. How about the derivative of 6x plus 7? You can do this in a couple of ways. I would not go back to the definition. We're doing shortcuts now. Easiest way to do this is say, this is a line. 6x plus 7 is a line. The tangent line to a line is a line, so the answer is the slope, 6. Or you could use the derivative of a sum as the sum of the derivatives. Take the derivative of the first part, the derivative of the second part. Derivative of 6x, 6 sits there while you take the derivative of x. Derivative of x is the derivative of x to the 1. The 1 comes down times x to the 0, so that's 1. Plus the derivative of 7 is 0, and that gives you 6. You see, that's not always the quickest shortcut. It's sometimes easier to just think, what is it that we're dealing with? All right, now we get to some hard ones. What's the derivative of the product of these two things, x minus 2 and 2x plus 3? Now, before we do this, let's just take some room up here, this little box. Now I want to calculate the derivative of something we already know the answer to. What's the derivative of x times x? Well, x times x, x squared, and everybody knows the derivative of x squared, 2x, right? What if you took the derivative of the first one and the derivative of the second one and multiplied them? You get the derivative of x, that's 1, and the derivative of x is 1. 1 times 1 is 1. The derivative of x times x? Obviously not. The derivative of x times x had better be 2x. We've done that already. So what this is telling you is that when you've got a product, you cannot take the derivative of the first and the derivative of the second and multiply them together. That's wrong. We'll learn how to do the derivative of a product in the next lecture. So what do I do when I have a product now and I don't have this product rule that we're going to learn about? Well, the answer is the only thing you can do is to multiply out that messy product. Foil it, in other words. So you're going to get x squared, 2x squared, and then plus 3x minus 4x is minus 1x, and then minus 2 times 3 is minus 6. So the derivative of that is not too hard. We take the derivative of 2x squared. The 2 sits there and watches. The 2 comes down. So 2 times 2 is 4 times x to the 2 minus 1 is 1. Minus derivative of x is 1. And then minus the derivative of 6. 6 is a constant, so that's 0 derivative. So 4x minus 1 is my final answer. That is the derivative of this quantity. Okay? Let's try one that looks a little harder, at least to some people. So I want the derivative with respect to t of the fourth root of t minus 4e to the t. How are we going to take the derivative of that? Well, whenever you see a radical, turn it into exponents. So this is the derivative with respect to t of, this is nothing more than t to the 1/4 power. And then the rest of it stays the same. Right? Just change radicals into exponents, the equivalent exponent. So now you take the derivative of t to a constant power using the high school rule. So you get 1/4 times t to the 1/4 minus 1. Now you have to start getting good with arithmetic. 1/4 take away 1 gives you negative 3/4. You get used to doing this after a while. So that's the derivative of the first. Now I have a difference, and there's a rule of derivatives that we talked about that says the derivative of difference is the difference of the derivatives. So I get a minus. Now I need the derivative of 4e to the t. The 4 sits there while I take the derivative of e to the t, and e to the t is an exponential function. So the derivative of e to the t is e to the t back at you, not t e to the t minus 1. Why? Because that t is a variable. It's the independent variable. And so e to the t is an exponential function, not a polynomial. So the derivative of an exponential function is an exponential function back again. E to the t has derivative e to the t. And that's our answer right here for the derivative. Okay? Let's do another one that looks kind of nasty, and it is a little. What's the derivative with respect to x of square root of x plus x divided by x squared? Now some of you are thinking, oh God, I got to use the quotient rule. And we haven't even learned the quotient rule yet. Well, no, we're not going to use the quotient rule. We don't know it yet. Furthermore, there's too many x's here. I think I want to simplify this before I try to take the derivative. So what is this in exponents? This is x to the 1/2 plus x to the 1 divided by x squared. And now I can split this into two fractions with a common denominator. So this is the derivative with respect to x of x to the 1/2 over x squared plus x over x squared. So all I did here was split this one fraction into two fractions with the same denominator. That's legal. That's how you add fractions. But now the derivative of a sum is the sum of the derivatives, so I can take the derivative. Oh well, wait, before I do that, let's simplify one more time. I've got the derivative of x to the 1/2 over the derivative, excuse me, I've got x to the 1/2 over x to the 2. Law of exponents that says x to the a over x to the b is x to the a minus b. So I just subtract the exponents, and I've got x to the 1/2 minus 2. 1/2 minus 2, 2 is 4/2, so that's going to be x to the minus 3/2. And there you got x to the 1 divided by x to the 2. That's going to be x to the 1 minus 2, or x to the minus 1. And now you've got the derivative of a sum, which is the sum of the derivatives. So I take the derivative of the first guy and the derivative of the second guy and add them together. And here each of these guys is an x to a constant, so the high school rule applies. Minus 3/2 x to the minus 3/2 minus 1, which is going to be minus 5/2. And then plus the derivative of x to the minus 1, which is going to give me a minus 1 times x to the minus 1 minus 1, x to the minus 2. And that's our final answer. Okay, so it's not as bad as it looks. All right, how about one that uses a different variable? What's the derivative with respect to u of the square root of 2 times u plus the square root of 3u? Well, what's the square root of 2? In a word, it's a constant. So what we're looking at here is the derivative of a sum, which is the sum of the derivatives. So I can take the derivative of the first guy and the derivative of the second guy and just add them together. What's the derivative of a constant times u, where u is the independent variable? Well, it's just that constant. Square root of 2 times 1. The derivative of u is 1. Okay, now I don't know what this next one is, so let's just keep the derivative with respect to u of this mess, square root of 3u. But instead of square root of 3u, why don't we write this as square root of 3 times square root of u? We can always do algebra as long as it's done correctly. Square root of 3 times square root of u is square root of 3u. That's how you multiply radicals. But now I'll write square root of u as u to the 1/2. So this is square root of 2 plus the derivative with respect to u of square root of 3 times u to the 1/2. And now we can take the derivative of this guy using the high school rule. So we get square root of 2 plus the square root of 3 sits there while we take the derivative of u to the 1/2. The 1/2 is going to come down, so we're going to get 1/2 times square root of 3, or square root of 3 over 2 times u to what power? U to the 1/2 minus 1 when we take the derivative, which is going to be minus 1/2. And that's it. Final answer. Okay. One more with funny variables, funny letters in them. Let's say we wanted the derivative of something with respect to v, the change, the instantaneous rate of change relative to v of a e to the v plus b over v plus c over v squared. Okay, the question here, first of all, is what's A, what's B, what's C? They didn't tell us. What's V? Well, V is the independent variable. That's the thing that we're taking the derivative of. How do you know it's the independent variable? Because it says here, take the derivative with respect to V of this mess. So V is the independent variable. So what does that make A? Well, they didn't tell us, but you're supposed to assume, if they don't tell you, that A is constant relative to V. Similarly with B, similarly with C. And what about E? Well, E is that number that we all know 2.7 about. So we're ready to do this. Well, except now we got to say, how are we going to do this? Is this a quotient rule problem? Well, no. Actually, for those of you who know the quotient rule, forget it. It's much, much easier to do this problem by turning this all into exponents. So this is the derivative with respect to v of a e to the v plus b v to the minus 1 plus c v to the minus 2. And now it's very, very easy to take the derivative. The derivative of the sum is the sum of the derivatives. Derivative of the first guy, the a sits there while you take the derivative of e to the v with respect to v. And the answer, of course, is e to the v. The exponential function is equal to its own derivative. What's the derivative of b v to the minus 1? B is a constant, so it sits there. The derivative of v to the minus 1 will be minus 1 times v to the minus 2. So we're going to end up with minus the b that's sitting there times v to the minus 2. And then here, what's the derivative of the third term? That minus 2 is going to come down, so we're going to get minus 2. The c is still sitting there watching. And then we multiply by v to the minus 2 minus 1, which is minus 3. That's it. That's the derivative. Easy stuff. Okay. Let's talk about finding the equation of a tangent line again. So here's the problem. Find the equation, or an equation, of the tangent line to the function y equals the square root of x, I'm sorry, got it wrong. Wrong way around. X minus square root of x. Now, the equation of the tangent line, but I don't want it at every point. I want it at this point, at the point 1, 0. A quick reality check. X equals 1 gives us 1 minus square root of 1, which will be 0 for y. So yeah, 1, 0 is on the curve. By the way, we should have an idea of what this curve looks like, real quick. What does the graph of x minus square root of x look like? Well, the domain is only positive numbers, so you can't plug any negative numbers in here. When x is 0, you're getting 0. That's pretty easy. And when x is 1, you're also getting 0. So at 1, you're getting a value of 0. Now, here's a question that you might not have thought about. Which one's bigger, x or the square root of x? Well, if you think about the graphs of the two things, x is the diagonal line, y equals x, goes through 0, 0, 45-degree line. That's y equals x. What's the graph of the square root look like? Well, the square root starts at 0, and it's a sideways parabola. Now, this sideways parabola actually has a tangent line here at 0 that is vertical. So it comes in here like this. So if you superimpose these two graphs on each other, here's x. And see, the thing is that when you are down below this point, if your x is less than 1, the square root is bigger than x. You can try that on your calculator. Try the square root of any number between 0 and 1. Like, what's the square root of 0.7? Put that into your calculator. Compare it to 0.7. Turns out the square root of 0.7 is bigger than 0.7. Square root of 0.1 is bigger than 0.1. Square root of a half is bigger than a half. Until you get to 1, and then they're equal. And then the number x will be bigger than its square root, just like the number 9 is bigger than the square root of 9. But it's reversed when you're in before 1, between 0 and 1. Okay, so what that means is that x minus square root of x is going to be negative in here because square root is bigger. So the graph is going to look something like this in here. And then when x is bigger than 1, then x gets to be bigger than the square root, and from then on it's positive. So the graph out here will grow, but who knows how. Okay, but the question is, what's the equation of the tangent line to that graph at this point, at the point 1, 0, right there? So the tangent line probably looks something like that. How do I get the equation of the tangent line? Well, first thing I need is the slope, and then I need a point. I've got the point 1, 0. So all I need is the slope, but the slope of the tangent is the derivative. So I need the derivative of this function. We call this function f of x. I need the derivative of that function, and I don't even need it at every point. I need it only at 1. Now this is a little bit weird. I could find the derivative of f at 1 using the definition, limit as h goes to 0, blah, 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 blah. But I'm not going to do that. That's a lot of work and very painful with something like this. What I'm going to do instead is I'm going to find f prime at x. This is the derivative at any x. So I will do that by looking at this function as f of x equals x minus x to the 1/2. And the high school rule tells me what the derivative of that is. 1. Derivative of x to the 1/2 will be 1/2 x to the 1/2 minus 1, which is minus a half. So this is the derivative of f at any x. You see, the answer depends on x. No surprise. The slope, the tangent line is negative here, positive here, 0 somewhere in there. Okay, but the question is, what's the slope of the tangent line when x equals 1? Well, that's just f prime at 1. So I just plug in 1 in here. So that's going to be 1 minus a half times 1 to the minus a half. But 1 to any power is 1. So this is 1 minus a half, which is a half. So the slope of the tangent line to this curve at 1 is 1/2. So this is my m, but I want the equation of the tangent line at this point, 1, 0. So I've got my slope, I've got a point, I'm in business. I can write the equation as y minus the y value, which in this case is 0, equals m, which is 1/2, times x minus the x value, which is 1. And that's it, folks. Now, in some of these problems, it actually says put the answer in the y equals mx plus b form. Well, this one would be pretty easy. Y equals 1/2 x minus a half. But as far as I'm concerned, I will ask you on an exam for the equation of the tangent line, and you can write that equation in any way you want. And so this is perfectly good. Yeah, of course, you can drop the minus 0. If you leave the minus 0 in, I promise I will not take off any points. In fact, I like it because it tells me where you got it from. You got it from this point right here, and I can see that. Okay. Well, I guess there is one other thing I'd like to talk about. This is getting late. But we should talk about the nth derivative. Right? We know what the second derivative is, the third derivative, the derivative of the derivative. We can play that game now with functions. Let's play that game with this function, f of x equals 1 over x. But I'm going to write it as x to the minus 1, so I can use the high school rule to calculate the derivative. So the first derivative is minus x to the minus 2. What's the second derivative? Well, you take the derivative of that, the minus 2 is going to come down, canceling that minus, and it's going to be plus x to the minus 3. Oops, I lost the 2. It's going to be 2x to the minus 3. Okay, what would the next derivative be? You could write that as f triple prime if you wanted, or you could write it, once you start getting a lot of these primes up here, it gets too hard to count. So you just put the 3 up there, but not entirely as an exponent. You put it in parentheses. So this is the third derivative. That's what that means. And so the derivative would be the derivative of the second derivative. That's going to be minus 6x to the minus 4. I shouldn't have written minus 6. I should have written 2 or minus 2 times 3 times x to the minus 4. Because I'm going to keep going. What's the fourth derivative? The fourth derivative will be the derivative of the third derivative. The minus now up here is going to cancel the minus here. So it's going to be 2 times 3 times 4 times x to the minus 5. What's the fifth derivative? Well, take the derivative of that. That's going to be minus again. 2, 3, 4, 5 times x to the minus 6. So you could probably guess what the nth derivative is going to be at x. Well, it's plus or minus depending on whether n is even or odd. So I could write it. If I really want to be fancy, I'd do it this way. This is one thing if n is even, and it's something else if n is odd. So when n is even, like the fourth derivative, and you notice you get a positive here, and so you're going to get 2 times 3 times 4 times dot 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 all the way out to n. Right? The fourth derivative, 2 times 3 times 4. The second derivative, 2. The sixth derivative would be 2 times 3 times 4 times 5 times 6. So you just multiply all the way up to n times x to the minus, well, the power here is 1 more than n. So it's minus the quantity n plus 1. That's if n is even. And if n is odd, you just put minus and then write the same thing. 2, 3, 4, dot, 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 n times x to the minus n plus 1. Now this quantity, 2 times 3 times 4 times everything up to n, that has a special name. It's called n factorial. It's usually written 1 times 2 times 3. We didn't have the 1 because I just dropped it. Times 4 times dot, 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 all the way out to n. So you multiply all the numbers together from 1 to n. That's n factorial. That number will come back and haunt you in later courses. In any case, we've all suffered enough. Good night.